In today's video, we're going to be learning about the fundamental theorem of calculus. This is arguably the most important thing you'll learn in all of Calculus 1. This theorem lets us find the precise answer to any definite integral in all of calculus, so we will definitely need this bad boy. And there's actually two fundamental theorems of calculus, or more so, two parts of the fundamental theorem of calculus. Let's talk about the first part. The theorem states it's the area under the curve defined by the integral from a to b, those being constants or variable numbers, of f of x dx is equal to f of b, so f of b minus f of a. And this can also be written as f of x from a to b. Let's talk about this a little bit because this is extremely important. So obviously a and b are our bounds of our integral. A and b being here, they get plugged into here. This capital F represents the antiderivative of our function. Say that this f of x was 2x, the integral or the antiderivative of 2x is x squared. So then we plug in a and b for x and then subtract the b value from the a value, and that would give us our area under the curve, or the answer to our definite integral. It can also be written with this line here, so you'd write x squared here, which was our antiderivative, from a to b. Let's do a couple examples. It's pretty easy to figure out once you do a couple of them. Let's start with something easy. Let's do the definite integral from -2 to 1 of 4x dx. First, we can pull this constant out of the integral, so this now turns into 4 times the integral from -2 to 1 of x dx. And now that we just have x dx in here, we can take the antiderivative of x. Using the power rule for integrals, this will equal 4 times x squared divided by 2. Remember, our power rule for integrals is x to the n plus 1, all divided by n plus 1. In this case, our power here is just 1. We don't have to write it because anything to the power of 1 is just itself, but there's an invisible little 1 right here. So x to the 1 plus 1 is x squared divided by 2. And then we just need to multiply that all by 4. We can simplify this down a little bit to make this 2x squared. And then of course, plus c. Now whenever we use the fundamental theorem of calculus, we don't have to worry about this plus c. So what we're going to do is we're going to write our little line here. Our a value is this bottom value, which is -2, and our b value is up here, 1. And now we just need to plug in 1 and -2 into here using our fundamental theorem of calculus. So let's write that down here. F of b is plugging in 1 for x, so this is 2 times, and I'll use a different color here to distinguish the value we're plugging in here, 2 times 1 squared minus 2 times, and then our a value, -2 squared. Now simplifying this down here, 1 squared is just 1, and 2 times 1 is just 2. And now for the second part of our equation, -2 squared is 4, and then -2 times 4 is -8. So you subtract 8. And then we get an answer of -6. And this is our answer to the definite integral from -2 to 1 of 4x dx. Now, it may seem a little weird that I wrote a -6 here. Remember, whenever we actually find the answer to a definite integral, we're finding an area, and negative area just doesn't make sense. Well, don't worry, it's a lot easier to explain with a drawing why this number ends up being negative. Let's draw our little graph down here in the corner. And remember, we're finding the area under the curve 4x dx. So let's draw that here. I guess we'll draw it in blue. Looks something like that. Now let's draw our points on the graph. This is -2 and this is 1. So if we draw some dotted lines here to show our boundaries, we can fill that in. Let's fill it in with a different color to make it even more distinct. We have this area here plus this area here. This little area here is 2, we got that here, and this area here is 8, but since it's on the negative side or above the line here, it's not actually area defined under the curve, it's area defined above the curve. So technically we have to subtract that area to get -6. So that's why that answer ends up being -6. I know it's a little bit counterintuitive, but that's what the answer is. Let's do a couple more examples. Let's now find the area of the definite integral defined from -π/2 to π/2 of cosine x dx. Well, first let's see if we can simplify anything. There's nothing we can pull out, there's nothing to divide, there's nothing to substitute, which we'll actually get into our next lesson. So we basically just have to take this integral as is. Now, fortunately, we know that integrals are the antiderivative, so we just need to go backwards from cosine. So what can we take the derivative of to equal cosine? That's right, taking the derivative of sine equals cosine. So the antiderivative of cosine is sine. So this is just sine x dx plus c defined from -π/2 to π/2. Once again, let's use our fundamental theorem of calculus to solve this problem. This is now equal to sine of, and plugging in our b value of pi over 2, we get sine of pi over 2, sine of pi over 2 minus sine of negative pi over 2. Now, using our unit circle, we can easily simplify this down. First of all, sine of pi over 2, which is right here at the 90-degree angle, is just 1 in the y direction, so this sine of pi over 2 is just equal to 1. Now, sine of negative pi over 2 is the same thing as sine of 3 pi over 2. We start at 0 and then go here, or you can go all the way around to 3 pi over 2. It'll end up being equal. If our line is going straight down and we know our circle has a radius of 1, sine of negative pi over 2 is negative 1. But we're subtracting negative 1, so this ends up just being 1 plus 1, which is equal to 2. And that's the area bounded by negative pi over 2 to pi over 2 of cosine of x dx. This is so much easier than all that Riemann sum stuff we were doing in the last lessons. If you haven't watched those yet, you should, because you need to understand what's actually going on when we take integrals. But this is much easier, and I highly prefer this, that's for sure. Now let's talk about the other part of the fundamental theorem of calculus. The second part of the fundamental theorem of calculus states that if f, our function, is continuous on a to b with the closed brackets, then taking the derivative, or in this case d dx, of our integral of f of x dx is just equal to f of x. In other words, the derivative undoes the integral, and the integral can undo the derivative. We've called integrals antiderivatives for a long time, but the whole point of this theorem is that they are opposites to each other. They do each other's inverse and can undo things that we've done in the past. This comes in a lot of handy many times in calculus, especially when you get into something like differential equations. So this is extremely helpful, and you absolutely need to know this. Like I said, the fundamental theorem of calculus might be the most important thing you learn in all of Calculus 1. But let's do a couple examples using this problem. Now, there is one other part of this theorem that we do need to talk about. The bounds here are not really a to b. The bounds could also be a to x. Now, why did we throw an x in here? That's a great question. If we throw in an x up here, usually our f of x is defined with a different variable, say something like t. And this x can change our variable from t back to x and get our original f of x function. Now, in order to actually apply this, x has to be the upper bound, and just x. Nothing else, just x, and it must be the upper bound. We'll talk about that in our first example problem. In this example, we want to find the derivative of the integral bounded by 2 to x of t squared minus 4t dt. What is the derivative of this function? Now, that may sound a little bit nonsensical at first. We have an integral here. Why are we looking for a derivative? Well, as we just talked about, the derivative can undo the integral. So if we take the derivative of this, we can get rid of the integral and find the derivative of this function as is. Note that our x is the upper bound of this function, and therefore there will be no issues here. We'll get more into that in our next example, but for now, let's solve this one. All we got to do is take the derivative of this function. d dx in this case, since our variable is x, what we're looking for, of the integral from 2 to x of t squared minus 4t dt. With our derivative and integral canceled out, this turns into, and you might think that it turns into t squared minus 4t, but since we do need to change it back to x, this actually changes into x squared minus 4x. And that's the derivative of this integral. Not too bad, right? Basically just got rid of it and changed the variable. Boom, we're done. It was really easy. Let's do another example problem. And this one is a little bit tougher, but still not too bad. Let's find the integral of x to 3 of secant squared u du. Now you may notice we have a little bit of a problem here. Our x is the lower bound and not the upper bound. And as stated before, we need our x to be the upper bound of this integral. Fortunately, integrals provide us a very easy way to switch the bounds. All we gotta do is put a negative sign in front of this integral. So this will now change into the negative integral of 3 to x of secant squared u du. And now we can just use a derivative to undo this integral and figure out what our derivative of this function is. Let's do that now. Since we are looking for x, we just take the derivative with respect to x of the negative integral from 3 to x of secant squared u du. Now that our derivative and integral cancel out, we simply get negative secant squared x. And that is our derivative. Remember, we just needed to switch our variable from u to x. And since we have x in here, we can just switch it up and we're all good. We're gonna do one more example, and it's a little bit tougher, but it's still not too bad. I'll walk you through it, don't worry. In our last example, we need to find the derivative of the integral from x squared plus 4x to 0 of 1 over t dt. Now this time, our x is not only not the upper bound, but there's a bunch of other stuff all around it. So we can't just use this even if we flip the bounds like we did before. But we can substitute something in for our x value in order to make it so that way it's just a single variable. So we're gonna actually let u, this variable u, equal to x squared plus 4x. These will be equivalent, and then we can rewrite this integral as the integral from u to 0 of 1 over t dt. Now we're going to need to remember this for later. We'll talk about that when we get to it. Now we can just flip the bounds. Once again, we can just make this integral negative to flip the bounds. So let's do that now. I'm going to go up here. So this will be the negative integral from 0 to u of 1 over t dt. Now what we got to do is take the derivative of this. And since our u variable is the one within this integral, we need to take this derivative with respect to u. This now turns into the derivative with respect to u of the integral, the negative integral from 0 to u of 1 over t dt times du dx. Now we haven't multiplied by this du dx before, and the reason we're doing that is we're taking the derivative of u with respect to x. This will allow us to switch our integral from u back to x. Now of course, with this integral and this derivative canceling out, we just have to replace our t value with u, and this will end up being negative 1 over u. But now we got to multiply by the derivative of u with respect to x. So we just need to take the derivative with respect to u of this x value. We already know what x equals, so we can just put in x squared plus 4x. Now to finish off this problem, we're going to move up here. I apologize for this not being super organized. So let's now just take the derivative of x squared plus 4x. That should be pretty easy. The derivative of x squared is 2x. We take our 2 to the front and then subtract 1 from the power. And then remember, the derivative of anything just times x is just the coefficient. So we can remove that x and we get negative 1 over u times 2x plus 4. Now we need to convert this u back to our x squared plus 4x. So this will now turn into negative 1 over x squared plus 4x times 2x plus 4. Now all we got to do, oh, hold on, let me put a multiply symbol there. Now all we got to do is put this into our numerator since we're multiplying by this, and we'll get our final answer of negative 2x plus 4, all divided by x squared plus 4x. And that's the derivative of our integral from x squared plus 4x to 0 of 1 over t dt. I hope you guys enjoyed this video and got some use out of it. If you did, consider subscribing, and if you want to learn more calculus lessons, consider checking out the playlist I've linked here. I'll see you guys in the next video.